Okay, good afternoon. It is Saturday afternoon. Actually, it's still Saturday morning. So I've spent most of the morning trying to condense down what I usually do in about three 80-minute class periods into one video. And, well, here it is. So we've already talked about mean, median, and mode. We already got that. We've talked about standard deviation, which tells us how spread apart data is, or another way to look at it is when does a certain data point look different, statistically significantly different than another data point. And what we talked about, and we're going to revisit our girls a few times today, we talked about the average height of a girl, at least I think we did. Anyway, we're going to do that today. In high school is 5 feet 4 inches. And we talked about the standard deviation being 2 inches. And, so if a girl is somewhere between, 5'2" and 5'6", pretty average. And no one would really notice that that person is particularly short or particularly tall. If we get above 5'6", maybe like to 5'7", 5'8", 5'9", or certainly 5'10", 6 feet, we start to recognize that that particular girl is way taller than the rest of the girls, and they are different. They're outstanding. And there aren't very many of them. And so let's talk about that in terms of the normal distribution curve, aka the bell curve. The reason is because it looks like a bell. So here's the deal. When you collect data about a characteristic, such as height, from a large group, you find that most of the group is near the average, or the mean, and small numbers are far from the average. So again, let's talk about our girls here. The average height is about 5'4", so we know that most of the girls are going to be somewhere in the area of 5'4". We're going to draw this in much greater detail in a few minutes. So most of the girls are in the area of 5'4", and you can see that this up here is the higher percentage. So the higher it is, the higher percentage. So there's a high percentage of girls that are, in this range, 5'2" to 5'6". Now when we talk about girls that are particularly tall, we have much lower percentages. So maybe we're out here at like 5'8", and maybe there's like 5% of the girls are like 5'8" or something like that. And same thing down here. Not such a big percentage for girls that are particularly short. So, and again, this goes for anything. Height, weight, salaries at a company, distribution of tips over a series of, 20 Friday nights. Some Friday nights are going to be getting good tips. Some Friday nights, not so good. And other Friday nights are going to be kind of in the middle, kind of average. So if you take a big enough sample, it's going to turn out this way. It's really pretty cool. Take a small sample, it doesn't quite look like this. Okay, so let's jump over here. And so if the group is large enough and chosen randomly, that's the key here, chosen randomly, we will get this nice bell curve. If, again, we wanted to find the average height of an American male, and the only people that we measured heights of were centers in the NBA, well, that wouldn't be a very randomly selected sample, and that would not give us a very accurate mean, and in fact, everyone would be way over here, and everyone else would be way down there. So, so it's key that we select randomly. Chosen randomly is key. It turns out that the numbers turn out to be amazingly standard. So when we choose randomly and we choose from large enough, we get this cool bell curve, and we get some certain percentages that go along with this. So as you might imagine, the very middle here is the 50th percentile, which means that 50%, again, if we're talking about heights of girls, 50% of the girls would be shorter than 5'4", 50% of the girls would be taller than 5'4". And the way we represent the mean is by X bar, which you saw in one of the videos. So X bar, X with a little line over it, X bar, that's the mean. And again, 50% of the people are at the mean. So then we talked about standard deviation. So again, sticking with our girls here, our standard deviation was 2 inches. So if we go 2 inches above, that makes 1 standard deviation. If we go 4 inches above, that's 2 standard deviations. If we go 6 inches above, that's 3 standard deviations. We can see that there are some certain percentages that go along with this. So if we want to know how many girls are between 5'4" and 1 standard deviation away, 5'6", 34% of the girls are going to be in that range. And again, choose large numbers, choose randomly, that's what's going to happen, 34%. These are well calculated, well established numbers. It's not like, well, maybe it's 35 this time. Nope, it's 34. If it's large enough and selected randomly, it's 34%. The mean, again, is still 5'4", and we want to know, well, how many girls are between 5'2" and 5'4"? Well, you guessed it, it's 34% because it's symmetric on both sides. If we want to know how many or what percentage of girls are between 5'6" and 5'8", it's exactly 13.5%. Same thing down here, 13.5%. And so we got 5'4", 5'6", 5'8". What percentage of girls are above 5'8" but below 5'10"? 2.35. 2.35%. And then above 5'10" is going to be some very, very small number over here. And the same thing goes down here. So we got 13.5 between 1 standard deviation and 2 standard deviations. So here we are at 5'4", 5'2", 5 feet 0. So the percentage of girls between 5'0" and 5'2", 13.5%. And we're going to use this whole table here, this whole diagram, to help us to answer some other questions. Okay, so as we've seen these percentages here, we can kind of expand them out a little bit and say, well, you know, the percentage of the population or a group that is within 1 standard deviation, +1 or -1, of the middle, the mean, is, add them up, 68%. So 68% of people are considered to be average. So again, within 2 standard deviations. Remember I talked about if we get, 1 standard deviation. If we get past 1 standard deviation, in other words, past 2 inches, we start to go, that person looks unusually tall, or that person looks unusually short. They're not average anymore. They're either above average or they're below average in their height. So the middle here is 68%. And if we want to figure out how many or what percent of the group is between is within 2 standard deviations of the mean, in other words, 2 4 inches up, 2 4 inches down, that's 2 standard deviations, that's 95% of the population. 95% of the group will be captured between these two, +2 and -2 standard deviations. So 95% of the girls are 5'4", +4 inches, -4 inches. So between 5'0" and 5'8", 95% of the girls fit in there. So that means 2.5 are over here and 2.5 are over here. So a very small percentage of girls are, very tall or very short. And that's the same thing with everything else. Again, if we're talking about the salaries, and not the salaries, the tips, on a given Friday night, on a whole bunch of Friday nights, most of the time you're going to be right in here. Maybe, I don't know, maybe make $50 in tips. But one Friday night, a couple of very large parties come in, and they spent a lot of money on food and drinks, and they give you a monster tip, and so you get a tip that's way out here. Maybe it's like $120, which is $70 more than your average, than your typical tip. So that ends you up way out here, and so 95% of the time you're going to be between here and here, but every once in a while, you're going to get that monster tip that's way out here. Or every once in a while, you're going to see that girl that's 6 feet tall or 6 feet 2 or whatever. They're going to be out here. But 95% of the time, it's between -2 standard deviations and +2 standard deviations of the mean. Okay. And I didn't mention this yet, I guess, but if we want to find out what percent is within 3 standard deviations, right? This is 1, 2, 3 standard deviations. 99.7% of a randomly selected large group will be between -3 standard deviations and +3 standard deviations. So again, in terms of our girls here, 3 times 2 is 6. So from 5'4" up to 5'10", and 5'4" -6 inches down to 4'10". So between 4'10" and 5'10". 99.7% of the girls are going to be between 4'10" and 5'10". So it's a very small percentage, obviously, of girls that are above 5'10" or shorter than 4'10". Okay, so those are the percentages for our normal distribution curve. So we can use those to help us to find the percent of any group that is above or below a certain value. And again, we're just going to stick with girls here because, you know, we're familiar with that that concept, and everyone has experience with that sort of thing. So, so here is our bell curve with all of our percentages stuck in there, and all the heights that we already talked about. So again, the mean is 5'4". That's X bar. That's the one in the middle right here, right? And this is 1 standard deviation. So this is plus 1 standard deviation. Above, this is minus 1 standard deviation. That's 1 standard deviation below the mean. So let's start answering some questions here. What percentage of the girls are taller than 5'4"? Well, we know that 5'4" is the mean. It's the middle. So 50% of the girls are taller than 5'4". I'm going to put that in green just because. 50% of the girls are taller than 5'4". What percentage of the girls are shorter than 5'4"? Well, 50% are shorter than 5'4", so that's pretty obvious. All right, let's get to something a little more tricky here, though. Shorter than 5'6". All right, so here we are at 5'6", and we know that 50% is the middle, and we know that 5'6" is right here, and we're going to have another 34% in here. So the number, or the percentage of girls that are shorter than 5'6" is 50% plus 34% makes 84%. 84% of the girls are shorter than 5'6". Now I want to talk briefly about percentile because that goes right into this. So if you remember your SAT scores, and maybe you saw your score, but you also saw your percentile. And maybe your percentile was, I don't know, 67th percentile. What that means is you scored better than 67% of the people taking the SAT that time. If your percentile was, I don't know, 23rd percentile, that means that you scored better than 23% of the people who took the SAT at that time. So percentile is always what percent is below where you are. So what's the percentile then for a girl that's 5 feet 6 inches tall? Well, she's in the 84th percentile because 84% of the girls are shorter than she is. And obviously, 16% of the girls are taller than she is. Okay. So let's do taller than 5'8". Well, again, we're going to start in the middle instead of at the end because we know what the middle is. It's 50. So taller than 5'8". Well, here's 5'6", here's 5'8". So I got 50% plus 34. So we're going to do a little work here. So 50 plus 34 plus 13.5. So how much is 50 plus 34 plus 13.5? Well, that is 84, 94, 97.5. So 97.5% of the girls are shorter, right, because it's left, right, less than that. So 97.5% of the girls are shorter than that. That leaves 2.5% of the girls that are taller. 2.5% of the girls are taller than 5'8". Not so many, not a big percentage. Okay, how about shorter than 5'2"? So again, here we are at 5'2", and again, we're going to start right in the middle at 50, and we're going this way. So we're going to remove 34%. Right here, we went 50, and we're adding these on, right? Because we're trying to figure out how much area is below here. So we started at 50. We take away 34, and that tells us what's left over here. So 50 minus 34 is 16. So I'm just going to write that down here. 50 minus 34, when we go that way, 16% of the girls are shorter than 5'2". Okay, so that's using the bell curve with all of these standard sorts of numbers on there. So this is all fine and good, just as long as the person or the data point or the salary or the tip or whatever it is that you're talking about lands exactly on one of the standard deviation values. Again, so when we're talking about girls here, we're talking about 5'4", 5'6", 5'8", 5'2", 5'0", an even number of inches. What happens if we have a girl who is not one of those even number of inches? There's got to be some way to figure things out for her, and there is. So this is great if all the girls are heights with even inches and no fractions. So if you're 5'4", or 5'6", or 5'8", good, easy. We just go back to that chart that we had just a minute ago, and you're all good. But what if someone is 5 feet 5.5 inches tall? Well, what we need to do is we need to figure out how many standard deviations is she above the mean. Well, we know that someone who's 5 feet 6 inches is 1 standard deviation above the mean because standard deviation is 2. Well, this person's only 1.5 inches above the mean, so where are they? Well, we need to figure that out. So we need a bit more precision, and that is what the z-score is going to tell us. So the z-score is simply the number, looks like I'm writing in green again, the number of standard deviations above or below the mean. Obviously, a positive standard deviation is going to be above the mean. A negative standard deviation is going to be below the mean. So the z-score just tells us how many standard deviations. So it may not be just a whole number like 1 or 2 or 3. It could be maybe you're like 1.5 standard deviations above the mean, or maybe you're negative 1.3 standard deviations below the mean. So it doesn't have to be a whole number, and in fact, if it's a whole number, then generally we can use that other table, that chart that we just looked at. But if it's not, we got to use z-scores. Okay, so the z-score is actually a really simple formula here. So let's talk about the things we already know, and then we'll talk about the thing that is a little unclear. So z is obviously going to stand for z-score. X bar, we already know that means the mean value. This is the mean, the average, or the mean, right? It's the same thing. SD stands for standard deviation. So then X is just the data point that we're thinking about. So in this case, when we're talking about a girl here who's 5 feet 5.5 inches tall, what is her z-score, or how many standard deviations above the mean is she? Well, we're just about to calculate that. Well, actually, we're going to do one for 5'5" first. So find the z-score for 5'5". Well, actually, this one's going to be pretty easy, but we're going to run through the formula anyway. So we're going to do z equals, so 5'5". It's actually going to be convenient for us. In this case, it's pretty simple, but just to keep things maybe more useful, it's going to be convenient to turn this just into inches. So 5 feet is 60 inches, plus 5 more is 65 inches. So a z-score for 5 feet 5 inches, so that's going to be 65 inches. Minus, well, we know that the mean is 5'4", aka 64 inches. So that's 64 right here. And we know the standard deviation is 2. So 65 minus 64 is 1 over 2. And generally we express these as decimals. So someone who is 5 feet 5 inches is 0.5 standard deviation positive. Positive 0.5 standard deviations. In other words, they're half a standard deviation above the mean. Okay. And yeah, so let's do a couple more of these. So let's do a z-score for 5 feet 9.5 inches. Well, again, we already know that 5 feet is 60 and 9.5 is going to be 69.5. So we got z equals 69.5 minus, the mean is still 64. The standard deviation is still 2. And my calculator's over here. So we're just going to do some subtracting and some dividing. So we got 69.5 divided by, or minus 64 is 5.5, divided by 2 is 2.75, Just want to make sure I'm right here because I don't want to give you some wrong information. So 5.5 divided by 2 is 2.75. Okay, so our z-score is positive 2.75. And this is all convenient because our standard deviation is 2, but ordinarily, obviously, our standard deviation would be some crazy number like 3.798 or something like that. You know, it's never going to come out to be something like this. Well, in this case, it did. So z-score for 5 feet 1.5. Well, again, easy enough. Z 5 feet 1.5 is 61.5 minus 64, still divided by 2. So this is going to be negative 2.5. So negative 2.5. So now we can see a z-score that's going to be negative. Divided by 2 is negative 1.25. So that's our z-score, negative 1.25. Okay, so let's do these with some context. So Bob works for a company. He makes $90,000 a year. The average salary at his company is $82,000 with a standard deviation of 5,000. What is Bob's z-score? No problem. Same formula, easy stuff. So Bob, this is the data value that we're interested in, so that's 90 Gs, minus the x bar, or the average, so that's 82,000, divided by 5,000 is the standard deviation. So we just do the stuff here. So we got 8,000 divided by 5,000 is 1.6. So Bob's z-score is positive 1.6. Pretty simple. Same kind of situation right here. Yep, that's it. Good. Okay, so this is just a contextualized problem. So there it is, 1.6. It's still the same, though. It's the same formula. Okay, so z-scores are actually used to determine percentages and percentiles from a table. And this table I'm going to show you is actually a very condensed sort of table. The table that is generally used, it has many more columns, many more values, but we're just going to simplify our lives by using a simplified version of the table. All the points and data that's given in the table is accurate. It's just there's not as many data points and as much as many columns and so on in the table. It's just a smaller table. Okay, so here is our table. We're not going to be able to look at all of it all at once. But, so let's take a look at our z-scores, and let's start with one that we already know a great deal about. Let's start with a z-score of 0. In other words, we are 0 above the mean. We are 0 standard deviations below the mean. We are actually right on the mean. And no big surprise, that's the 50th percentile. 50% below, 50% above. So let's jump up to 1 standard deviation above. And right here, and again, this is one that we should be familiar with because we already talked about it. It is 84.13, 84.13th percentile. And again, what we remember from our bell curve back in the day, let's see if I can grab that page right here. If we are 1 standard deviation above the mean, it's 50 plus 34. And these are kind of approximates here, right? 34%. So 50 and 34 is 84%. Well, here we are, 84.13%. And let's just pick another random one here. Let's do negative 0.75. So if we are 3/4 of a standard deviation below the mean, that means that there's going to be 22.66% of the group that's going to be below that particular score. So here's our table, and this is what it tells us. This is a percentile. Again, percentile is the number or the percent of the group that is below a certain score. All right, so here's our table. I'm going to leave this right on the desk here because we're going to need it for the problems that are coming up. All right, so it says determine the percentile, the percent below, and the percent above for a given z-score. So we've already talked about the z-score of 0. But I'm just going to answer all the questions though. So determine the percentile. Well, that's right in the table. So that's the 50th percentile. We could even write 50th if we wanted to. And the percent below. Well, the percent below is identical to the percentile, so it's 50% below. And the percent above. Well, all you need to do is subtract from 100 and you get the percent above. And in this case, they're all the same because that's what it is on the mean. Okay. Z-score of 1. So we're actually going to look that up from the table here, and we're going to get our percentile. And actually, we already looked it up, but we're going to look it up again just to make sure we have the exact number here. And it is 84.13. So a Z-score of 1. So that gets us right here. Right here is X bar, and here is 1 standard deviation above. So what we're looking for here, the percentile, we're looking for this area right down here. Everything below, all the way down there. We're looking for that area. And as it turns out, we already figured that area out because we just looked it up. So the percentile is the 84.13 percentile. That's the percentile. I'll put tile because I've run out of room here. Do it this way. Percentile. And what's the percent that's below? Well, percentile and percent below are exactly the same, so that's below. And then percent above, well, again, just subtract from 100, so that's going to be 15.87. So 15.87% is above. Okay, so same trick down here, 1.2. This one we're going to have to look up again. So we pick this up and we find 1.2 on the table. So there's our z-score. We got 0.4, we got 0.8, we got 1, 1.2 right there. 1.2 is some number that I literally cannot read. It looks like it might be 88 point, I don't know. I'm going to go with 49, but like I said, I really can't see it. I'm going to try to zoom in. And oh, I did. Yeah, good. 88.49. Good for me. So this is 88.49. So that is our percentile there. So z-score of 1.2 is 88.49 percentile. And how many above? Or how many below, I mean? You guessed it. 88.49% below. And what percent is above? Well, that's going to be 11.51. 11.51% above, right? We just subtract from 100. And the same, let's do, so we already got this positive stuff going on, so let's do a negative one. Let's do negative 0.4. So again, jump into the table, negative 0.4, let's see if we can find it. There's negative 1, negative 0.6, negative 0.4 is 34.46. 34.46. So the percentile is 34.46. The percent above, yep, you guessed it, 34.46. And the percent above, sorry, I meant below. And the percent above, just subtract that from 100, and we have 65.54, I think. 65.54% is above. Again, just using the table and finding percent from the table. Okay. All right, so now let's put this in context. So we want to find the percentile, percent above, percent below for a given situation. So here we have some girl who's 5 feet 7 inches tall. We already know the mean is 5'4", and we know the standard deviation is 2. So what we need to do is we need to find out her z-score. And then once we know the z-score, we can go to the table. So z equals 5'7", so we already talked about that being 67, minus 64 divided by 2 makes, I'm going to put that right over here, 67 minus 64 is 3 divided by 2, which is 1.5. So 1.5, we jump into the table to get our percentile from the z-score here, and it's right here, 93.32. So, percentile, 93.32. What percent is below this? Same thing, 93.32. Percent above, you just subtract from 100 and you get 6.68. 6.68% above. And that's it. So just find the z-score from the context, just find the z-score using the formula. Once you got the z-score, into the table, get your percentages and percentiles. Simple stuff. Okay, one more of these. And then, yeah, we got 2 more things to do after that. So sorry this video is long, but like I said, I'm packing in 3 lessons into 1 video. So salary, 80,000. The mean salary at this particular company is 90,000, and the standard deviation is 6,000. So again, we find the z-score. This person's going to be below average here. So we got 80,000 minus 90,000 over 6,000. So 80 minus 90 is negative 10 over 6. So 10 divided by 6 equals 1.6 repeating. So negative 1.67. So in a normal standard table, not the abbreviated abridged one that we're going to use, we'd be able to find 1.67. But we don't actually have that luxury right here, so we're going to do some approximating. So 1.67 is, and it's negative by the way, right? Negative. So we're going to do the closest one, which is going to be negative 1.7, which is right over here. Negative 1.7 is 4.46. 4.46. All right, so that means that Bob here is, what's his percentile? Percentile. He's in the 4.46th percentile. Percent below. Yep, you guessed it, 4.46% below. And percent above is 95.54. 95.54%. So I'm going to guess that Bob probably doesn't talk about his salary very much at that company. Okay, there it is. So finding the percent and percentile in context. All right. So now we can also use our z-score to help us to find a data value. So let's say that for whatever reason we are able to find out that some girl who has a height with a z-score of 1.3, and we know that the average is still 5'4". So we'd like to find out her height. Well, her height is actually going to be the x in our formula, right? Remember our z-score formula, x minus x bar over SD. So we're just going to plug in the numbers and find this girl's height here. So the z-score is 1.3. That goes right here. The x bar, or the x, we don't know, but we do know the x bar. It's 64. And the standard deviation is 2. So we have this little equation to solve, pretty simple. So we're just going to multiply by 2. So 2 over here gets us 2.6 equals x minus 64. Add 64 over, and we know that this girl is going to be 66.6. That's unfortunate. That's an unfortunate height. 66.6 inches tall. Poor girl. Anyway, there it is, 66.6 inches tall. So using the z-score to get a value, simple application of the formula. Okay, we are on to our last page. Yep, 2 sides of a page and we're done. Okay, so hopefully our dog is a little more fortunate than our girl that we just talked about. So we have a z-score that is negative 0.8. We know that the average is 35. We want to know how heavy is this dog. Well, let's figure it out. So negative 0.8 equals x we don't know, minus 35, that's the mean, and the standard deviation is, crap. I didn't give a standard deviation for this. All right, let's make up the standard deviation. Standard deviation is, let's say, 7 pounds. I just made that up, obviously. This is all just made up. So I just forgot to put in standard deviation into the given information in the problem. So we just do our stuff here. So 7 times -8 is negative 5.6 equals x minus 35. And then we're going to do 35 minus 5.6. Just making sure I don't get wrong answers here. 29.4. So x equals 29.4 pounds. So Bob's little dog weighs 29.4 pounds. Again, just a simple application of our simple formula here. Okay, so the last thing I want to talk about is confidence intervals. I'm going to need my calculator one more time, I think. So a 95% confidence interval from a survey. What does that mean? Okay, well, here in New Hampshire, we get lots of political stuff because we're the first in the nation primary. So there's polling that comes out all the time when presidential candidates are around. And so when they do a poll, they always do the poll and then they say plus or minus 4% or plus or minus 3% or something like that. And so what that means, let's say that we have a candidate and their popularity, let's say it's a survey about popularity, their popularity is 54%. And then it'll say in parentheses off to the side here, it'll say something like plus or minus 4%. So, and remember we said 54% here. So what that means is we are 95% certain that the real popularity of this particular candidate is somewhere between 54 minus 4, 50%, and 54 plus 4, 58%. So we are 95% confident that this candidate's real popularity is somewhere between 50 and 58%. Well, how come we're not 100% certain? How come we don't know? We just asked a whole bunch of people. We did. That's the key. We asked a whole bunch of people, but we didn't ask everybody. And so the fewer people we ask, the less accurate our poll is, right? If you just ask one person, I don't know, what's your, I don't know, who's your favorite candidate? Whatever, and it's, it's Bob. Well, Bob is 100% popular. Well, that's ridiculous. There are some people that don't like Bob. So again, the key here is always to have a large group, just like we talked about before, and got to be randomly selected. So the key here is that we need to have these large groups, and if we don't have large groups, in other words, actually, if we don't cover everybody, then we're going to have some sort of potential for error, potential for mistake. But we can get within 95% certainty. So we can say we're 95% certain that Bob's real popularity is somewhere between 50 and 58%. So that's the whole margin of error thing. All right, so that's what that means. All right, so here's a situation. So in a recent survey, 70% of the people, plus or minus 3, of those surveyed said soccer was their favorite sport. What I want you to do is I want you to write out, or I want us to write out, or we're going to write out I feel like I was going to put this on the page here. Yeah, okay, good. So I want you to write a statement about that. So here's the statement that we can write. Am I in green? Yep. So there is a 95% certainty that the actual favorite sport, the actual percent of people who chose soccer as their favorite sport, is between, so where are we here? 70% plus or minus 3. So 70 minus 3, 67%. And 70 plus 3, 73%. So we are 95% certain that the percent of people who actually believe soccer is their favorite sport is between 67% and 73%. So that's pretty good. So only 5% of the time are we actually going to be wrong right here. 5% of the time it could be like 75 or 60% or something like that. But, well, again, we're willing to take that chance here because the only way to get 100% certain is to survey every single person. And in New Hampshire, that's going to be 1.3 million people, and that's just going to take too long. So we take our chances and we go 95% certain. That's pretty good. I'll take that. I'll take those odds. So that's how to write one of those statements here. There is a 95% certainty, or we could say we are 95% certain that the actual percent of people who chose soccer as their favorite sport is between 67 and 73%. 70 plus or minus 3. Okay, so let's do one more of those. So in a recent poll, candidate B led candidate A by 57% to 43%. So we would like to make a statement about let's say candidate B here. Their likelihood of winning, 57%. So they are, so this is making believe that the election was held today. If the election was held today, how would the vote go? 57% to 43%. Okay, so what we want to say then is that candidate B would have gotten, so what we're going to say here is, we are 95% certain that candidate B would have gotten 57% plus or minus 4. So gotten between 57 minus 4 is 53%, and 57 plus 4, 61%, 61% of the vote. So that's pretty good. We are 95% certain that the candidate B would have gotten between 53% and 61% of the vote. So that's pretty good. Candidate B can feel pretty confident about where they're at. Let's say that this was 51 to 49 plus or minus 4. Well, 51 minus 4 is 47. 49 plus 4 is 53. So actually it would have been the other way around. So what we want here is we want to be able to say that the difference here is outside the margin of error. The margin of error is 4%. So if we drop 57 down to 53 and 43%, and we add that up to 47%, is candidate B still ahead of candidate A? And the answer is yes. So we say that this is a pretty significant difference in the two percentiles or percentages for the candidates because it's outside the margin of error. Subtract 4 from this one, add 4 to this one, and they don't overlap. So that means that candidate B is definitely ahead of candidate A. Unlike if it said 51-49, it's too close to call. Because if you add and subtract 4% from each of those numbers, they switch. And that leaves some uncertainty here. But we are 95% certain that the candidate B would have gotten between 53% and 61% of the vote. All right. So there is actually a formula, and it's a really simple one, to find a 95% confidence interval for a known survey size. If you know the survey size, n, then you just plug it in here, 1 over n, take the square root, and that's going to be your plus and minus percent, right? Just like we got here, plus minus 4%. So let's actually do that. So in a recent survey of 900 people, they indicated that math was their favorite subject. 35% of the people said that. Write a statement. Well, so what we're going to do here is we're going to do some calculating. So we're going to do 1 divided by 900. So we got 1 divided by 900 equals, then we're going to take the square root of that. So I'm going to raise that to the 0.5 power because that's the easy way for me to take the square root. And I get 0.03 repeating. 0.03 repeating, 0.03 repeating. So I'm going to turn that into a percent. So that's 3.3 repeating percent. I'm just going to write 3.3%. And so again, what I want to do is make the same kind of statement that we made up here. So we are 95% certain that the percent of people who chose math as their favorite subject is between, crap, I'm running out of room. Where are we here? 35 minus 3.3, so that's 31.7. Put it right up here. 31.7%. And 3.3 added on, 38.3%. So again, because we took a survey, we didn't ask everybody, but we asked a sample of people. We asked 900 people. And so that's why we don't have exact accuracy here. But we can be 95% certain that somewhere between 31.7 and 38.3% of the people think math or are certain that math is their favorite subject. So there you go. There is 3 lessons in 46 minutes. Sorry that took so long. Hopefully you were watching it in pieces. And yeah, I will have more review stuff later. But this is all you need. So you have all the information you need and you have your practice test. And yeah, if you got questions, just let me know and I can answer questions. Molly already answered a question and I did the problem for her, took a picture of it and posted it. So anyway, yeah, so be well, be safe, enjoy your weekend. It's not too hot and I'll see y'all on Monday.